Okay, guys, this is a lesson on the properties of rational functions. So this is kind of taking a different gear of what we've been doing. We've been dealing with polynomial functions, and now we're dealing with something called rational function. Rational function is just a very fancy way of saying fractions. So our equations now are fractions, where the top is a p of x, the bottom is q of x. So they're two different functions combined together into a division problem, but the top is a polynomial and the bottom is a polynomial. And more importantly, the bottom cannot equal zero because you can't divide by zero. All right. Some of the examples are like these, right? You have 1 over x, that's a rational function. 1 over x squared, that's a rational function. The top is a polynomial, the bottom is a polynomial, that's a rational function. In fact, your rational functions don't have to be a specific degree. The pattern is going to change and the pattern is going to affect your final graph and the shape of it. But that's what we're going to do in this lesson to see, oh, what happens when the top polynomial is bigger than the bottom polynomial? How do I get certain information from what's given to me? Okay, let's start with domain. Remember how we need to deal with domain. We need to know whether or not there are numbers that can't or cannot that cannot be. So the problem with the domain of these is that it says the domain of a rational function includes all real numbers except those that cause the denominator equal zero. Basically, your denominator cannot equal zero. But we haven't done things like that. So the trick is to go ahead and set your denominator equal to zero, solve for that, and that's what your domain cannot be. All right. So start with the first one. You have, it says write the domain of the following function in interval notation. So first thing you want to do is try to factor as much as you can from your original equation here, right? So our denominator now factors into x plus 2 and x minus 2. Okay, then you solve them separately. You have x plus 2 equals 0 and you solve. Once you solve, you get to the bottom of it, then you want to change the equal to not equal to because you can't equal to those two. Now, it's a little bit easier to look at this in terms of a number line, but gradually, if you don't need a number line to help you, you don't need to put the number line down. Number line is more like a training wheel for you, right? So if you put it on the number line, you can see it's everything else except those two dots. So for me, it's a lot easier to see the interval because I can see that my interval goes from negative infinity all the way to negative 2, pause, negative 2 to 2, pause, 2 to infinity, and therefore that is my interval notation of the domain of this function, okay? Similarly, you'll do the same thing on the next one. You start by factoring what you can, numerator and denominator. You always want it in most factored form, and then you can do whatever we want to do next with the equation, right? Then you take your denominator, set equal to zero, and remember, same thing. Once you set equal to zero and solve, these are the things that you cannot equal to, right? Again, the number line is suggested. You don't have to, but the number line is a little bit easier to see the interval, and therefore, in the end, you should be able to write your interval nicely with this. So this is the domain part of it, right? Now let's kind of switch gear a little bit and look at what we call asymptotes. So rational functions, they have a lot of times where your equation can't equal, right? So when your equation can't equal a certain number, your graph won't exist at those numbers. So there's a couple types of asymptotes. There are vertical asymptotes. These are the vertical lines here, right? These are called hard barriers because you cannot cross them. Your graph will get really, really close, so you're going to bend towards it, you're going to lean towards it, but you won't cross these vertical asymptotes. A horizontal asymptote is going this way. Now, horizontal asymptote can be crossed, so it's a soft barrier. So, it's more like an end behavior, like as it goes towards infinity, where you're heading towards. So horizontal asymptote is really a misnomer. We like to call it more like end behavior. And then there's a third type of asymptote, which is called the oblique asymptote, where it's like a diagonal line like this. And as you can see, our graph is still leaning towards those lines, but it's going to be slanted. So that's an oblique asymptote. All right. Most of the time I shorthand these. I call these VA, vertical asymptote, horizontal asymptote, HA, and oblique asymptote, OA. Right. And oblique asymptote is usually in the form of y equals mx plus b. It's a linear function, and you can graph this out using your knowledge of what linear functions can do. Okay. So how do you know what type you have, right? So how do you find the vertical asymptotes? The steps are simple. First, you simplify the function, you rewrite it, you factor as much as you can. And for now, we're going to deal with equations that, it won't simplify too much. You're just able to factor and set the denominator equal zero and solve. And this time we are setting it equal zero because these are the vertical asymptotes. These are where the domain cannot be. Therefore, these are your vertical asymptotes, right? So you take your denominator, set equal to zero, and then you solve, you get x equals negative 5. Therefore, your vertical asymptote is at negative 5. So if you were to draw this out, and you can use decimals or a graphing calculator to kind of help you see the picture, but see the picture is really helpful, right? the asymptotes won't really show up. When you graph it, it's not going to be in the graph. But you can see my graph is getting towards. This is your vertical asymptotes. You can tell that your graph is leaning towards it. And as you zoom out away from it, you'll see your graph is going to get closer and closer to that -5, but never ever crossing that line. So this side's going to get closer, this side's going to get closer, but again, closer, never touching. Okay. All right, same thing we're going to do to the next one. We are going to factor as much as we can. So we start by factoring. Oops, sorry, not that. Start by factoring the denominator, right? So you have x squared minus 5x equals 0. It's going to be x times x minus 5. So don't forget to set the first x equal to 0. So you get two answers here. So you have two vertical asymptotes, one at 0 and one at 5. So yes, the picture will look something like this. Once again, if you zoom in a little bit more, you will see you actually have a vertical asymptote here. See that 0, you're not going to cross. And then you have another one here at 5, right? It's a very interesting picture, and you will learn how to graph this later on, okay? Okay, let's move on. What about something like this? Again, same step. We take the denominator set equals 0, factor, and don't forget to solve. That 5x in the front will give you an answer, and the x minus 2 will give you another answer. So you have vertical asymptotes at x equals 0 and x equals 2. The graphs may change a little bit, but as you can see, we do have those two asymptotes here. Okay, now from this point on, I'm not going to show you graphs because it's not necessary right now. We're just trying to find the vertical asymptotes. And because also of what is happening in the numerator, your graph's not going to turn out as nice and as easy to spot the asymptotes. So right now, we're going to focus on the algebra of how to find these asymptotes. Okay. All right, so continuing with the next one, remember we're going to factor as much as we can. Well, in this case, the numerator is not going to factor really well, so I'm going to leave it as is, right? And then I am going to factor the denominator, which is what I did in the bottom here. I factor the denominator, and then I set them separately equal to 0, so I get the two answers here. Notice I'm not putting not equal because these are the asymptotes. So I'm going to say x equals 1, x equals 2 for my asymptotes. Okay, all right. You are welcome to pause right now and go ahead and work out E and F on your own. When you are done, then you go ahead and press play because I'm going to show you the answers to these problems. Once you are done, you can check. Before you do so though, pause. From part E here, you want to change that -6 to a +6. It will make the entire thing much better. We'll explain this later on, but right now just bear with me and change it to a +6. All right, so again, go ahead and pause right now and then work out these two problems to find out your vertical asymptotes and then press play again to check your answers. Okay, moving on to the next page here, we are looking at horizontal asymptote and oblique asymptotes, right? So we already figured out how to find vertical asymptotes, and now we're looking at horizontal or oblique asymptote. So when you're looking at your functions for the rational function, you're comparing the polynomial in the numerator and the polynomial in the denominator. Now, same thing we did before, we're looking at the leading terms. So the leading term of the numerator versus the leading term of the denominator, right? Now, the degree of the numerator, the degree on the top, is the n. So that is this part right here, the highest power in the top, right? And then the degree of the denominator is going to be m. So that's a degree on the bottom here, the highest degree here. Oops, sorry, I didn't mean to use that. I meant to use a highlighter. The degree is going to be m, all right? So when you're comparing the highest power on top versus the highest power on the bottom, if the top is smaller than the bottom, you're going to get y equals 0 as your horizontal asymptote. If they are the same, you simply take the leading term over the leading term. So you're looking at the coefficient. So a sub n over b sub m. So this is what we have here. The a sub m and the a sub n, b sub m. So that is going to be what you have, and you reduce that. That will be your horizontal asymptote. If the numerator is bigger by just 1, so right here, if the numerator is bigger than the denominator by just 1 degree, then the line of y equals mx plus b is going to be an oblique asymptote. More importantly, you have to do the long division. I know we talked about this. We do long division to find a quotient to figure out what the y equals mx plus b is. If the denominator is a nice linear function, like a nice x plus or x minus, you can get away with not doing long division and use synthetic and get that. You get the same result. Okay. All right. So in this case, what I'm going to do next is I am going to go over the A part and then you're going to do the B part, right? So we're going to do example 1 each, right? So first one here, you see that the top degree is going to be a 1, right? Because the highest power is 1. The bottom, the degree of the denominator is going to be a 2 because the highest power is 2. So since 1 is less than 2, your y equals 0 is your horizontal asymptote. Okay. Similarly, the next one, the top degree is 2, the bottom degree is 3. Since 2 is less than 3, y equals 0 again for your horizontal asymptote. Okay, in C here, you can see the top degree is 1, the power of x is 1, bottom is 1, so they're the same. Therefore, you got to take your leading coefficients, your 3x and x, right? And you got to reduce it out. So you're going to take 3x over x, reduce that to get y equals 3, and that is your horizontal asymptote. That's why I put HA there. Okay, similarly here, we have the leading coefficient over leading coefficient. So we have the top degree of 2 over top degree of 2, same bottom degree of 2. 2 is equal to 2. Therefore, you take your leading coefficients and you go ahead and reduce it out. And then you get y equals 2 is your horizontal asymptote. Okay, next one, your top degree is 2, but the bottom degree is 1. So you are bigger than the bottom by 1 degree, so you got to do your long division. So go ahead and look at this, remind yourself of how to do long division, but more importantly, the quotient, the answer here, this is going to be your oblique asymptote. So you're going to write that down, and that is your oblique asymptote, right? The 10 down there is your remainder. It really doesn't play anything in this case, okay? Has no role. All right. Same thing in the next one. Top degree is 2, bottom degree is 1. So you go ahead and do long division again. You're going to divide through. So make sure you look through the steps and understand how I got my quotient of 2x minus 1. Therefore, getting my 2x minus 1 to be my oblique asymptote. Once again, I want to remind you, it is totally okay to shorthand the asymptotes because it's really long to write. And sometimes I've missed a P or a T here. So A is totally fine. So HAVAOA. So horizontal asymptote, vertical asymptote, and oblique asymptote. Okay, now the practice problems here, we are going to see how this comes in play. You got to make sure you address everything, right? So it says find the domain and the asymptotes. So you're going to answer everything here. So remember, domain is to make sure you are taking the denominator setting equal to 0 and what it cannot be, right? But more importantly, we factor as much as we can first. So first thing I want to do is factor the equations. Then I take my denominator set it equal to 0. And I remind myself that those are the numbers I cannot be. And I remind myself using a number line if I need to kind of see the relationship. And therefore, this is my domain. Now, my vertical asymptote, I go back to what it's equal to. So you just go ahead and take your information here. Those actually are your vertical asymptotes. Then you compare the degree. The degree of top is 1, degree of bottom is 2. Therefore, 1 is less than 2. You have y equals 0 as your horizontal asymptote. Okay? All right. Now, go ahead and pause real quick. Try part B because it's very similar to part A. And then when you are ready, press play so you can see the answer to this part. Okay, now going to part C, this is slightly different, right? So again, I start by factoring as much as I can. The numerator factors, the bottom doesn't factor, doesn't matter, okay? So now let's go ahead and take the denominator and set equal to 0. So now I can see my vertical asymptote using my number line, and therefore I have my domain to be negative infinity to 1 and 1 to infinity. Okay, now remember, this is my vertical asymptote, which I will talk about in a minute, right? But I remind myself of the degrees. So the top degree, my horizontal asymptote is going to be 3x over x because that's my highest power on top over the highest power on the bottom. And therefore, my horizontal asymptote is y equals 3. And then don't forget to address the fact that you have a vertical asymptote at x equals 1. Okay? All right, same thing. Pause right now real quick. Go ahead and do part D, very similar to part C. And when you're ready, press play so you can see the answers being revealed. Okay, second to last, we have another example here. So again, we start with the same steps of factoring this out so we can clean up as much as we can. Numerator is factoring beautifully. The denominator doesn't need much work here. So go ahead and take your denominator, set it equal to 0 so that you can see that this part is for the domain. This part is for the vertical asymptote. From the same answer, we have two different things we can take away, right? Okay, so here we have our domain. I don't need the number line anymore, so I just go ahead and write the domain. And now I am going to write my vertical asymptote later, but I'm going to look at whether or not I have a horizontal or an oblique asymptote. Now, one thing I forgot to mention is that you will either have a horizontal or an oblique. You won't have both, right? So it's either a horizontal or oblique, or you have no horizontal asymptote. So those are your three options, okay? You won't have two of them at the same time, but you can have multiple vertical asymptotes. You can have infinitely many vertical asymptotes, which again, you'll see later, okay? All right, Because the top degree is 2, the bottom degree is 1, you're going to have to do long division to figure out what the your quotient is. Once you have your quotient, you can see that your y equals x is your oblique asymptote. And don't forget your vertical asymptote coming back to this part right here is going to be x equals 1. So again, don't forget that this came from the fact that this y equals x came from your quotient, and that would be your answer for your oblique asymptote. All right, last but not least, go ahead and work through F. Pause the video right here. Go ahead and work through F, and then when you're ready, press play and see the answers. Okay, so at this point, we are currently temporarily done with our rational functions, and we will definitely do more once I am back.